Hello everyone, we are presenting our research regarding minimizing the duck-bill curve with energy storage. This research was done by Nicholas Johnson, Jamil Balas, Saurav Singh, Zaid Anwar, and Harpal Diol.
California is at the forefront of becoming the first state to become 100% carbon neutral. There are problems, however, that come with being in the lead. There are a lot of unknown speed bumps that California has to overcome in order to attain 100% renewable energy generation. In 2018, California legislature mandated that by 2045 all sales of energy must come from qualified, renewable, and carbon-free sources. The closer we get to this date, the harder it is to become carbon neutral and fossil fuel free. Fortunately for California, there are already 14,359 megawatts of renewable energy available to use, and 64% of that comes from solar, with wind coming in at around 25%. However, solar energy is only available for a small window of time due to the fact that the sun sets and rises every day. The other sources of renewables, such as wind and geothermal, are available all throughout the day with a higher reliability and consistency. Unfortunately for us, the demand of energy does not line up with the massive amount of solar energy that California can produce. Ideally, solar energy should be available at the time of peak demand. However, when taking a look at the summertime power demand from previous years, we can see power needs that are upwards of 50 gigawatts. In order to have a chance at completing the vision of carbon neutrality and net zero fossil fuels that can fill the 50 gigawatts of peak power demand by 2045, California must incorporate a diverse array of renewable, reliable energy sources. To solve the problem of not having enough energy available at the time we need it, California can procure new forms of energy storage that can shift the renewable energy to a time when it's actually needed. What is the duck curve? The duck curve refers to the energy demand trend in California. On this chart, the demand curve is shown in blue and resembles the shape of a duck. Typically, we see high demand in the mornings. This demand drops off in the middle of the day and steadily ramps up in the evening. However, peak solar production is in the middle of the day when the demand is the lowest. This leads to solar curtailments in the summer because solar energy is not able to supply the peak demand. The main issue with introducing more solar and other renewables is that the peak supply and peak demand is offset by about 6 hours.
In order to overcome the problem of having inadequate renewable power at peak times, California has initiatives to shift renewable power use by integrating storage devices that delay the power use to when the demand is peaking. For example, California Assembly Bill 2514 tells the California Public Utility Commission to make a technical analysis of current power demand trends in order to come up with a timeline for the procurement of appropriate amount of electric energy storage. The CPUC determines that by 2024, 1,300 megawatts of storage in any form must be procured by the top three investor-owned utilities, PG&E, SDG&E, and SCE by 2024. Fortunately for us, at this time, we are just shy of that number and are already on track to installing more than 1,300 megawatts of energy storage by 2022. In addition to this order, all energy service providers in all counties in California are required to procure some sort of energy storage equal to 1% of their 2020 annual peak. More recently, the California Independent System Operator was told to oversee 3,300 megawatts of new electric capacity in the state of California, but then responded a year later saying that the urgency of new capacity is being undermined and suggested that 10,000 megawatts of electric capacity need to be established and built by 2024. The suggestion that any new electric capacity may include new generation techniques, but storage methods may prove more fruitful in the long term as it will stop the curtailment of certain renewable resources, accelerating the growth in our electric capacity.
Next, we have energy storage methods. The three main energy storage methods are chemical, mechanical, and thermal storage, which includes technologies such as batteries, hydrogen electrolysis, pump hydro, and concentrated solar plants. Battery storage, which is a chemical storage method, is gaining popularity and is being adopted in California out of the methods listed. Battery storage methods are typically on-site of renewable generation plants, such as solar farms and wind turbine fields. Next is hydrogen storage, which is also another chemical storage method. Hydrogen storage is where the generated renewable energy goes through a process of electrolysis, where hydrogen gas is the output of this reaction that can be further used for energy storage or to delay when the energy is available for the demand later in the day. Furthermore, a mechanical method of energy production is pump hydro. Pump hydro has been a method for some time now and is one of the less feasible methods as its cost and time of construction outweighs the power production of the system. Last, we have concentrated solar plants, which are used as a type of thermal storage method. It takes thermal energy and saturates dense materials that will hold energy for long durations. All of these methods of conserving energy for a later use are viable options and beneficial to mitigating the duck-bill curve. However, all of these methods also have their own scenario where they can play out in effective manners, regarding their cost of production and operation costs as well as total efficiency. Here we have battery storage. Battery storage is a popular method used for minimizing the duck-bill curve, as it can store energy and release it as needed or as scheduled over time, thus providing the reduced curtailment required. These storage facilities are typically on-site of the renewable energy production that feeds it, such as solar farms and wind turbine fields as discussed before. The batteries in the facility are stacked in a way for easy maintenance of a cell or for replacement as needed. Battery storage facilities are capable of being on a small or large scale, ranging from utilities ownership or community-based microgrid ownership. Also, due to the ability of controlling when and how much energy can be expelled from the batteries, we are able to use energy at the most demanding times. Controlling the outflow of energy also allows for blackout start operations, where the batteries can then power areas suffering from blackouts. Battery storage gives a chance for securing investments made into renewable energy production, as it allows for a precise way to use generated energy. Battery storage is approximately 75 to 85% efficient, which is higher than most. However, batteries can only charge and discharge to a certain limit to keep batteries at a healthy level. The low starting cost, as well as the great savings of up to $2 million in grid and fuel costs when using a 4 megawatt, 40 megawatt hour facility, provides a feasible means of storage for a cleaner, greener future.
Hydrogen storage. The process starts by generating hydrogen by itself. There are many methods to produce hydrogen, such as natural gas reforming, which revolves around taking a mixture of gases and then separating the hydrogen from it. Electrolysis, which separates water atoms by running a current through it. Fermentation, and liquid reforming. Once the hydrogen is separated, if electricity is wanted to be produced, then one way is mixing hydrogen with oxygen to react and produce water, some heat, and electricity, while another one is feeding hydrogen into an anode and an air mixture is fed into a cathode, which provides electricity. The range of efficiency to this method of generating electricity usually ranges between 25% to 80% of the energy produced, depending on the way we choose. If we choose the anode and cathode method, efficiency will range between 25% to 45%, while the other one has about 75% rate of efficiency. Although the efficiency and the electricity produced by this type can be amazing, it still costs about an estimated value of $2 million to build the hydrogen storage station that stores about 180 kilogram a day of hydrogen.
Over 90% of our worldwide energy storage capacity is in the form of pumped hydro. Pumped hydro is a well-understood technology that has been around for nearly 100 years. California currently has 7 pumped hydro storage plants that account for almost 4,000 megawatts of stored capacity. That is roughly enough stored capacity to power 3 million homes for an entire month. Pumped hydro storage can be both open loop or closed loop. An open loop system is connected to a naturally flowing source of water, whereas the closed loop system works in isolation. Pumped hydro takes advantage of gravitational potential energy by using power to pump water to an elevated reservoir. A mechanical turbine generates power as the water is flowing from higher elevation to lower elevation. On average, pumped hydro storage plants operate with about 80% round-trip efficiency, and some of the largest plants can store up to 3,000 megawatts of capacity. The storage duration is essentially unlimited, but it can only continuously discharge storage capacity for about 16 hours. The main factor holding back the construction of new pumped hydro plants is the long construction times of up to 10 years and the high initial cost of around $5,000 per kilowatt. However, once built, pumped hydro plants have a lifetime of up to 60 years. Pumped hydro storage has a low carbon footprint. However, there are still some environmental concerns because the construction of these large plants can disrupt the ecosystem and natural habitats in the area. Concentrated solar plants are a form of thermal energy storage. Instead of solar panels, concentrated solar plants use heliostats, which are movable mirrors that concentrate the sun's heat on a boiler. The unheated fluid is sent from cold storage tanks into the boiler and is heated to temperatures of up to 1,000 degrees Fahrenheit. The liquid is then stored in another tank and can be used to heat up water to create steam. Using a conventional steam turbine, this steam is converted into electricity. Concentrated solar plants, or CSPs, have been around since the 1970s and use several heat transfer fluids for thermal storage, such as water, oil, and molten salt. However, with the chemical properties of molten salt, we are able to store energy for a longer duration with an average daily heat loss of less than 5%. The efficiency of these concentrated solar plants is around 35% by the time the heat is converted into electricity. The concentrated solar plant in Solana, Arizona has a capacity of 1,000 megawatt hours and can continuously discharge for up to 10 hours. The construction of one of these plants can take anywhere from 3 to 5 years, depending on the size. To put it into perspective, the Solana CSP, which spans 3 square miles, costed around $1.45 billion and it took 3 years to construct. The typical lifespan for these plants is around 30 years. However, with proper maintenance, this lifetime can be extended. Concentrated solar plants have a low carbon footprint, but the main environmental concern is the damage to the ecosystem and natural habitats.
There are advantages and disadvantages to each form of energy storage. California has set the target for energy capacity. However, it is up to the stakeholders, such as utilities, private agencies, and customers, to evaluate the various forms of storage. In order for a stakeholder to select the energy storage that best suits their needs, there are several factors they must keep in mind. The maximum capacity is one important factor that may affect their decision. Pumped hydro has the highest capacity of up to 3,000 megawatts. However, lithium-ion batteries, hydrogen, and molten salt have much lower capacities. The stakeholder also needs to consider the cost of each form of energy storage. Although pumped hydro has a large capacity, there is a high initial cost of up to $3,000 per kilowatt. If the budget is tight, lithium-ion batteries have one of the lowest initial costs of around $600 to $1,200 per kilowatt. Discharge time is an also important factor for energy storage. Discharge time refers to the amount of time that the storage can consistently discharge its stored capacity. Pumped hydro and molten salt are able to discharge for long periods. However, batteries are typically only able to discharge for 4 hours. Hydrogen storage is a relatively new technology with varying discharge times. The lifetime of the energy storage technology must also be considered. Pumped hydro and molten salt have some of the longest lifetimes of up to 30 to 60 years. The lifetime for hydrogen storage varies but can also be extended to nearly 30 years. Lithium-ion batteries have a much lower lifetime of 1,000 to 10,000 cycles, which roughly translates to about 10 to 15 years. In order to maximize the amount of electricity from storage, you need to have a good round-trip efficiency, where lithium-ion batteries and pumped hydro have very, very high efficiencies at around 85%. On the other hand, hydrogen and molten salt are still least efficient forms of energy storage with an efficiency of around 40%. After discussing the different benefits and drawbacks of some of the popular storage methods, it is important to discuss how this data could impact California's decisions. Batteries and pumped hydro have the highest efficiency when talking about round-trip electric capacity. and batteries seem to be the cheapest in terms of cost per kilowatt. However, the lifetime of batteries is not nearly as close to how long a pump storage plant would last. For instance, Helms Pump Storage Plant east of Fresno, California, started its construction in 1977 and is still providing us with 1.2 gigawatts of electric power for a consistent 12 hours or more, depending on the demand. Batteries, on the other hand, have around 100 megawatts of capacity each, but may be expanded. In fact, projections made by Statista suggest that lithium-ion batteries costs will be cut by 46% to $110 per kilowatt hour in 2025. The difference between batteries and a pumped hydro facility is that batteries are typically unable to sustain their 100 megawatts of power for no longer than 4 hours. This becomes a problem when trying to mitigate the demand for power at those peak times mentioned earlier. Pump storage plants are believed to be the solution to the fast spike in power demand because of its high capacity and long-term power output rate. However, they are very costly and may take up to 5 years to construct, with the cost ever increasing. In order to fulfill the goal of reducing the duct bill curve, a large amount of power and storage capacity is needed. Pump storage is the strongest and longest lasting of the few options we have discussed today. However, many areas may choose to implement batteries or small hydrogen fuel cell facilities in order to have storage banks for their neighborhoods, industrial buildings, or supermarkets. The problem with hydrogen fuel cell technology is the storage method. For example, gathering hydrogen from an electrolyzer may not be ideal because of its volume limitations as well as its explosive properties. Hydrogen needs to be compressed with a hydrogen condenser, which can cost up to $50,000 each and is very loud. This is not something you would want in your local neighborhood, but could come in handy in other situations, like the newly expanding market for hydrogen-powered cars. Molten salt is the least economical of energy storage due to its low efficiency and large space commitments it requires. Tanks of molten salt are able to get up to only 600 degrees Celsius and fuels a steam turbine with its heat at a 35% round-trip efficiency. The benefit of molten salt plant is that it would have a very long shelf life for up to 30 years. This long lifetime may be useful because of the technology in this field may advance within the next 30 years, and we could be able to improve on its efficiency. But as of right now, it is the worst long-term contender.
In conclusion, in order to avoid a complicated issue such as the duct bill curve, a simple solution was found, which is to delay the use of power generated to a later time at which the demand for it is present. There are many ways that were mentioned to preserve electric power to use when needed. These methods were chemical, mechanical, and thermal. We had mentioned that thermal energy can be stored in concentrated solar plants, and mechanical energy in the form of pumped hydro, while chemical energy has two ways of storage, which are either batteries or hydrogen stations. Each one of these forms has its own efficiency levels and costs that make it better than the other. If these storage methods are utilized, California can absolutely reach its goal of 10 gigawatts of energy and even more with the lowest amounts of CO2 emissions and least harm the environment. We as engineers have the ability to design, create, and use these means to change not only our future, but the next generation's futures as well.
Thanks for tuning in to our presentation. We hope it was very informative. If you have any questions, feel free to contact us.